Welcome to DTH channel, lecture 4 of atomic and nuclear physics. This lecture is going to be about vector atom model and quantum numbers. I am going to organize this lecture in the following way: introduction about the lecture, Sommerfeld atom model, vector atom model, quantum numbers, and summary of the discussions we are going to have. In the previous lecture, we have discussed Bohr atom model, an important one in the history of atom in atomic physics, which throws many fundamental concepts about atom. This Bohr atom model is applicable only for hydrogen-like atoms, that is, atoms which has only one electrons in its outermost orbit. Sommerfeld model and vector models are the concepts which explains the fine splitting of spectral lines. Bohr's atom model introduced only the principal quantum number. Other quantum numbers which are in use in atomic physics and in modern physics are proposed by Sommerfeld and in vector atom model. Then size and shape of the spectral line of an atom is explained by the advanced models like Sommerfeld model, vector model, all these things. A spectral line emitted by an atom is based on the transition of the electrons in the atom. We know Bohr atom model proposed a concept of transiting electrons from higher energy level to lower energy level, while transiting from the higher energy level to lower energy level, radiations are emitted. Energy of those radiations are equal to the difference between the energy values of higher energy level and lower energy level. That is a fundamental concept in atomic physics to explain the energy and wavelength of the emitted radiation. Here in this lecture, you will know the other quantum numbers used to explain the radiation emitted. Sommerfeld atom model. This atom model explains the fine spectrum of hydrogen atom. The important postulates of Sommerfeld atom models are: the orbits may be both circular or elliptical. In Bohr atom model, only circular orbits are proposed, but Sommerfeld said that orbits can also be elliptical. When the path is elliptical, then for that ellipse, two axes are there, major axis and minor axis. When the length of the major and minor axes become equal, then the orbit is circular. This is the connection between Sommerfeld model and Bohr model. Then angular momentum of electron moving in an elliptical orbit will have values k into h by 2 pi. This concept has connection in Bohr atom model also, which is called quantization of angular momentum. An electron revolving in an orbit has an angular momentum equal to integral multiple of h by 2 pi. This is the quantization rule. Here in Sommerfeld model also that quantization rule is used. Here instead of n, k is there. This k is an integer except 0. Then the value of k can be 1, 2, 3, 4 like that. Then n by k is equal to length of the major axis divided by length of the minor axis. That k value is in denominator. When the denominator value increases, ellipticity of the orbit decreases. So n will become equal to k, then the orbit will become circular. Sommerfeld suggests that orbits are made up of sub-energy levels. This is another concept introduced by Sommerfeld. In Bohr atom model, Bohr said only about the orbits. He didn't say anything about the suborbits or sub-energy level. Sommerfeld propose that sub-energy level. These sub-energy levels are named as S, P, D, F, which we use in the electronic configuration of an atom. If you are asked to write the electronic configuration of atom, automatically you will go for 1s2, 2s2, 2p6, 3s2, like that. No. So those S, P, D, F are proposed by Sommerfeld. These sublevels possess slightly different energies. Bohr gave a quantum number n, which is called principal quantum number. This principal quantum number determines the energy of the electron and the value of name for the shell, K shell, L shell, M shell, N shell, like that. We are using electron shells. No, those shells are named based on the values of the principal quantum number. Sommerfeld introduced a new quantum number called orbital angular momentum or azimuthal quantum number, which determines the orbital angular momentum of the electron. Bohr proposed the orbital angular momentum, but here Sommerfeld gave a name for that orbital quantum number and used that in the calculation of explanation of spectral lines of atom. Coming to the values of connections between the principal quantum number and the orbital or azimuthal quantum number. You know that principal quantum number is n, orbital or azimuthal quantum number is L. There is a connection between this n and L. When for n is equal to 1, that L can have values n minus 1, 0, that is 1 subshell, 1s subshell. For n is equal to 2, then L can have values 1, 0 and 1. So for 0 the suborbital is 2s, for 1 the suborbital is 2p. Here the 2 denotes principal quantum number is 2. 2 denotes the principal quantum number is 2. For n is equal to 3, L can have values 0, 1, 2. So for 0 the suborbital name is 3s, for 1 the suborbital name is 3p, 3d subshell. For n is equal to 4, L can have values 0, 1, 2, 3. So 4 values are possible for 4 values are possible for L when n is equal to 4. So rule is framed connecting n and L. So L can have values between 0 to n minus 1. So if you have n is equal to 5, then L values can be 0, 1, 2, 3, 4. So 5 values are possible. So like that principal quantum number and orbital or azimuthal quantum number are connected by Sommerfeld atom model. Then when an electron jumps from one orbit to another orbit, the difference of energy depends on sub-energy level. In Bohr atom model, the difference of energy is set only between the original energy level. This difference of energy between sub-energy level explains the splitting of individual spectral lines of hydrogen, and thus fine splitting of spectral lines are explained by this Sommerfeld atom model. This Sommerfeld atom model could not predict the exact number of lines which are actually present in a fine spectrum, but it said the spectral lines can be splitted in more elaborated form. So this is the pictorial explanation of Sommerfeld orbitals. When n is equal to 1, L can have only one value, 0, then automatically the orbit will be in circular form. When n is equal to 2, L can have two values, 0 and 1. So for 0 it's a circular orbit, then for elliptical orbit, then for 1 it's a circular orbit. So as the L value decreases, elliptic ellipticity of the orbital decreases. That's the understanding from this pictorial explanation of Sommerfeld atom model. Here you can see L is equal to 0, L is equal to 1, then this one is L is equal to 2, then L is equal to 3. For the principal quantum number value, N is equal to 4. This is how Sommerfeld atom model throwed light on orbital or azimuthal quantum number. In Sommerfeld atom model, some defects are there. This model does not explain the behavior of system having more than one electron, and also it does not explain the splitting of spectral lines when it is passed through fields like magnetic field and electric field. So, the Sommerfeld atom model does not explain Zeeman effect and Stark effect. So, these are the drawbacks of Sommerfeld atom model. To overcome the drawbacks of Sommerfeld atom model, vector atom model came. This vector atom model basically deals with two fundamental features. They are space quantization and spinning electron hypothesis. These are the two features of vector atom model. This vector atom model also deals with angular momentum of an atom, which is a result of the combination of orbital and spin angular momenta. In vector atom model, the spin concept is introduced. So, we got the orbital angular momenta and spin angular momenta. Combining these orbital angular momenta and spin angular momenta gave the total angular momentum of an electron present in an orbit. Coming to the space quantization, which is one of the feature of vector atom model. The angular momentum is a vector quantity, so automatically it will have direction. This direction should be specified completely. Angular momentum of an electron, direction of the angular momentum of electron should be specified completely. To specify the orientation or direction of an orbit, a reference is required. Here in vector atom model, the direction of the magnetic field applied to the atom is chosen as the reference line. With respect to the direction of the magnetic field, in what direction the orbit is oriented, that can be calculated. Then the rotating electron about the nucleus forms a current loop. This is a very basic concept in electromagnetism. A charged particle moving in a circular path will form a current loop. So, a magnetic moment will be there for the charged particle. That magnetic moment is mu is equal to I into A, where I is the current, amount of current flowing in the loop, and A is the area vector. Energy of the loop field system is given by U, atomic energy, magnetic energy is equal to the magnetic moment into the magnetic field. Magnetic moment of an electron and the dot product of magnetic moment and magnetic field, which gives the magnitude of the magnetic moment and the magnetic field into cos theta, where theta is the angle between the magnetic moment and the magnetic field. As such, classically any energy value between minus mu b to minus plus mu b is possible for the current loop. An electron orbiting around the nucleus in an atom possesses angular momentum. That angular momentum is denoted by L, which interacts with external applied magnetic field P. According to quantum theory, there are fixed directions of magnetic moment. L into L, L dot L of magnetic dipole formed by closed loop motion of electron about nucleus. So, magnetic dipole is formed by the closed loop motion of electron about nucleus with respect to the magnetic field. The magnetic moment and angular momentum of the electron can be related as mu is equal to E by 2me into L. So, this is the relation connecting the magnetic moment and angular momentum. This relationship is true from both classical and quantum mechanical point of view. Since discrete directions of magnetic moment are allowed, as such the direction of angular momentum will also be quantized in space. So, the quantization refers the projection of angular momentum along the z direction, which can have discrete values only. So, space quantization means projection of angular momentum along the z direction. The orbital magnetic quantum number ml gives the direction of the angular momentum and tells the possible component of angular momentum in the z direction, that is in the field direction. Here in space quantization we are learning about the orientation of the orbit. To know about the orientation of the orbit, direction of the magnetic field is taken as reference. So, orbital magnetic quantum number gives the direction of L and tells the possible component of angular momentum in the field direction. So, the phenomena of quantization of L in the direction of magnetic field is commonly known as space quantization. This is how space quantization can be learnt. Then the direction of magnetic field is along the z axis. As such, the component of angular momentum along z direction is also given as Lz is equal to ml. The ml can table the values from minus L to plus L including 0. As we have seen in Sommerfeld atom model, that L can have values based on the value of principal quantum number. When principal quantum number is 2, L can have values 0 and 1. Here the angular momentum or magnetic quantum number can have values between minus L to plus L including 0. So, the discussion about space quantization of orbits and possible components of angular momentum can be understood with the following example. Let us calculate the allowed projection of the angular momentum for total angular momentum. Capital L denotes the total angular momentum, and this L is the orbital or azimuthal quantum number for L is equal to 2. The L can visualized as a vector lying on the surface of a cone. So, this pictures will give you a clear explanation about total angular momentum of the orbit electron. So, this is the actual direction of the total angular momentum. Then this is the z direction where magnetic field is oriented. Then the component of the total angular momentum is nothing but m suffix L h cross. So, here Lz is equal to 2 h cross, 1 h cross, 0, minus 1 h cross, minus 2 h cross. This minus 1 h cross is for the value of ml, magnetic quantum number minus 1. This magnetic quantum numbers can have values between minus L to plus L. So, this pictorial explanation is for L is equal to 2, azimuthal quantum number L is equal to 2. So, azimuthal quantum number L is equal to 2 correspond to a particular sub energy level. According to Sommerfeld model, for n is equal to 1, L can have values 0 and 1. So, for n is equal to 3, L can have values 0, 1, 2. For L is equal to 2, these are the possible magnetic quantum number. Then these are the directions of the orbits of the electron. So, vector atom model explains the orientation of the orbits in space, which is called space quantization. So, this is for ml is equal to 2, ml is equal to 1, this is for ml is equal to 0, then this is for ml is this orbit is ml is equal to minus h, ml is equal to minus 2h. The possible values of ml for L is equal to 2 can be minus 2, 1, 0, 1, 2, hence L is at the direction of orientation of angular momentum along its direction mlh, which is equal to minus 2h minus h 0 h 2h. So this figure shows the space quantization of the orbits. Next concept in vector atom model is spin quantization. The spin quantization was explained by Goudsmit and Ugenberg in the year 1925. This spin, they proposed that electrons have spin about an axis through its center of mass, and further it has both angular momentum and a magnetic momentum. The spin of electron is analogous to the planetary motion about the sun in our solar system. Quantum mechanical treatment has demonstrated that spin of electron should be quantized. As such a new quantum number phi has been introduced, that is spin quantum number. Earlier we have principal quantum number, orbital quantum number, then total angular momentum quantum number, magnetic momentum quantum number. Now the fifth quantum number is spin. Spin angular momentum is related with the spin quantum number as S is equal to total spin quantum number S is equal to square root of S into S plus 1 into H. The spin can be either clockwise or anti-clockwise, either up spin or down spin. Like that also you can connect the spin values. So it can take values plus half or minus half. So S is equal to square root of root 3 by 2 into H. This is the total spin quantum number value for an electron. Then component of, earlier in space quantization we have seen the component of total angular momentum. Now in spin quantization, component of spin quantum number along the direction of magnetic field is governed by quantum number S is equal to MSHS, where MS is the spin magnetic quantum number. The spin magnetic quantum number can take values 2s plus 1. As such, MS can have two values, which is plus half or minus half. This is the thing about vector atom model. Based on this vector atom model and other atom models, quantum numbers are explained in atomic physics. The quantum numbers are principal quantum number denoted by N, orbital quantum number denoted by L, spin quantum number denoted by S, total angular momentum quantum number denoted by J. In addition to these, three other quantum numbers have been introduced in vector atom model. Those are magnetic orbital quantum number ML, magnetic spin quantum number MS, and magnetic total momentum quantum number MJ. These are the quantum numbers existing in atomic physics or in modern physics. Coming to the principal quantum number. This principal quantum number represents the serial number of atomic shells starting from the innermost. So N can have only positive integer values excluding 0, like 1, 2, 3. The name for the shells for these principal quantum numbers will be K shell, L shell, M shell, N shell. So principal quantum number is used to represent the outermost electronic shells. Next quantum number is orbital quantum number, small l. The orbital quantum number small l can have values from A to n minus 1, where n is the principal quantum number. For example, if n is equal to 3, then orbital quantum number can have values 0, 1, 2. Conventionally, we call this L is equal to 0, S electron, L is equal to 1, P electron, L is equal to 2, D electron, L is equal to 3, F electron. So orbital quantum number is used to represent the suborbitals or sub-energy levels. Then spin quantum number. Spin quantum number has only one value, that is half. Based on the rotation of the spin, that is up spin or down spin, this half value can be taken as minus half or plus half. The next quantum number is total angular momentum quantum number, J. The total angular momentum quantum number J is the sum of orbital angular momentum L and spin quantum number S. As such, J can have value L plus or minus S or L plus or minus half, because S can have values only half, can have value only half. The next quantum number is magnetic orbital quantum number, M suffix L. As discussed previously, the magnetic orbital quantum number ML can have values 2L plus 1. For example, for L is equal to 2, ML can have values minus 2, minus 1, 0, 1, 2. So, totally 5 values are there for magnetic orbital quantum number if the azimuthal quantum number value is equal to 2. This is the use of magnetic orbital quantum number. The next quantum number is magnetic spin quantum number, MS. The magnetic spin quantum number can take values 2s plus 1. We know that s is equal to half, and hence ms can take values 2 into half plus 1 is equal to 2 in total. So, the values of ms can therefore be minus s and plus s, or minus half and plus half. The next quantum number is magnetic total angular momentum quantum number, MJ. The total momentum quantum number of an atom is a vector quantity and is the vector sum of orbital momentum L and spin angular momentum S. That is, J is equal to L plus S. We define the quantum number total angular momentum Mj known as the magnetic total angular momentum quantum number and specify the orientation of this total angular momentum in space with respect to the z axis. According to quantum mechanics, this total angular momentum quantum number can have values square root of j into j plus 1 into h, and js is equal to mj into h. So, the possible values of mj are 2j plus 1, that is, mj can take values from minus j to plus j, including 0 in integral steps. Now, jz is equal to Lz plus or minus Sz. This is how the total quantum number, total angular momentum quantum number can be obtained by summing the angular momentum quantum number and spin quantum number, which implies that Mj is equal to Ml plus or minus Ms. Now, Ml is an integer and Ms is plus or minus half. As such, Mj will have the half integral values only. The Mj, Ml and Ms can have the maximum value J, L and S respectively. This is how the quantum numbers in atomic physics can be learnt. So, in this lecture we have learnt about Sommerfeld atom model. This atom model introduced the sub-energy levels. Vector atom model introduced the orientation of orbit in space and the concept of spin for electrons, orientation of the spin of electron in space. All these things are explained by the vector atom model. Then vector atom model explains the Zeeman effect, which we are going to see in the next lecture. Then other quantum numbers in practice in atomic physics, like principal quantum number, azimuthal quantum number, angular momentum quantum number, magnetic angular momentum quantum number, magnetic spin quantum number, magnetic total angular momentum quantum number. Like that, different quantum numbers are there in practice in atomic physics to explain the transition of electron from one energy level to other energy level, to give out the spectrum colors in nature, in practice. These are the things we learned from this lecture. You can learn more things about this concept by referring these books and websites. Thank you.